Hello everyone, welcome back to Physics 425. Last time what we were talking about was the micro-canonical ensemble. And so the idea was we had a bunch of replica systems all isolated from one another, but each of the systems had to satisfy certain constraints on, say, the volume and temperature and energy. And one of the things we worked out was that the entropy of the isolated system was equal to kb ln of W, where W was the number of quantum states that satisfied all these constraints. What we're going to do today is we're going to talk about another ensemble. It's the canonical ensemble. And the difference between what we talked about last time and what we'll talk about today is that we're going to have a bunch of replica systems, but the systems are going to be able to exchange energy with one another, whereas before, all of the replicas were isolated from each other. Okay, so we imagine an ensemble of systems, all with identical number of particles, volume, maybe they're in a magnetic or electric field, and so that's the same as the microcanonical ensemble, but what we're going to do today is we're going to say all of these systems are in thermal contact with each other instead of being isolated from one another. So as a whole, the ensemble acts as a thermal reservoir that maintains a constant temperature. So it maintains the temperature of each member of the ensemble or each system in the ensemble at a constant value T. So we can try to draw a picture of what this might look like. So we imagine that there's a whole bunch of systems that are in contact with one another. So I'll draw this as if there's maybe 100 systems or something like that, on the order of 100. But we're really imagining like a really huge number of systems, Avogadro's number of systems. So for the ensemble, the total energy is constant. So the ensemble itself is isolated from the outside world, and its temperature is constant. So constant total internal energy and constant temperature. But if we were to identify, say, a particular member of the ensemble, say over here, what we would allow is that there could be energy exchanged with its neighbors. Okay, and so the idea is that the internal energy of system A can vary. This canonical ensemble is useful because there are many situations in which experimental measurements are done where the system temperature is held constant. So this is useful because in many experimental measurements, we keep the sample or system temperature constant. Okay, so as I said, the ensemble is isolated from the rest of the universe. And because it's isolated, it has a constant total internal energy, which we'll call UT. Okay. However, energy can pass from one system in the ensemble to another. Okay, so let's consider system A, the one we colored red, with internal energy UA, and the remaining system as the reservoir. So the remaining system is the entire ensemble except system A, with internal energy. So this is the reservoir. So it's going to be the total energy of the ensemble minus whatever the energy of system A is. Okay, so in this case, the combined system has a certain number of configurations or quantum states available to it. And so, let's see. So how many quantum states does it have? So this is going to be a function of whatever the energy of system A is, and so it's going to be the number of quantum states available to system A, and so that's WA, and multiplied by the number of quantum states available to the reservoir, which is at energy UT minus UA. So it has this many accessible quantum states. Okay. Okay, so now let's imagine the following. Let's imagine we take system A and we choose one particular state for that system, and so that's fixed. So if one particular state of A is chosen, so just for the sake of notation, let's say we choose state phi I with energy, the energy of system A is equal to EI. So in that case, we've chosen a particular state, then WA at energy EI is equal to 1. So that's fixed. We've chosen that quantum state, and the total number of quantum states available then is WA at EI, which is 1, times WR at UT minus UA, but UA now is chosen to have an energy EI. Okay, and so this is WA at energy E1 represents system A in state phi I with energy EI. Okay, so now let's go to the first law of thermodynamics. First law of thermodynamics, which says that the change in internal energy is dq or TdS, and then there's the work term minus PdV. Okay, so if we rearrange, let's solve for t. So we could write 1 over t as ds du at constant volume. So if we work at constant volume, the PdV term vanishes, and we can isolate for 1 over t. Now, for the entire reservoir, which is an isolated system, we can use the result from last time, which was that the entropy is kb ln of w. And so we could say if S is kb ln w, then we get a kb d ln of wr. Let's work with this reservoir, du at constant v. And so we say since for the reservoir, S is equal to kb ln wr. Okay, so let's just continue. Then, so therefore, all I'm going to do is just divide by kb. 1 over kbt is equal to d ln of wr dur. So that's the internal energy of the reservoir. All right. And since t is equal to a constant, then what we could, so you might worry here that what have we done? We have said that, here, let's put an R for the reservoir. We're assuming that the reservoir is an isolated system, but of course it exchanges energy with system A. But we're assuming that the reservoir is so massive that whatever tiny energy that it exchanges with system A doesn't have a serious effect on its total energy because it's made up of so many other replica systems. So we can, to a very good approximation, treat this as an isolated system, and then we can use the result from last time that S is kb ln w. Okay, so temperature is constant, and so that means we can simply rearrange this expression and integrate. So if we multiply by dur and integrate, we have 1 over kbt, the integral of dur. The t, we don't have to worry about keeping it inside the integral because it's a constant. And then what's left over on the right-hand side is the integral of d ln of wr. Okay, or let's see, ur over kbt is going to be equal to ln of wr, and then there's going to be an integration constant. I'm going to choose to write that integration constant as minus the ln of gamma, where gamma is some constant. So this whole thing is our integration constant. Okay, so if we solve for wr, this is going to be equal to, so we add the ln gamma and then we exponentiate, we would get gamma e to the ur over kbt. Okay, so let's go back here, and we had this expression that W at energy EI was WR, the number of quantum states of the reservoir, which is something that we just calculated, at an energy of UT minus EI. Okay, and so therefore WEI, which is equal to WR UT minus EI, what I'm going to do is I'm just going to use this expression above and substitute in for the energy of the reservoir UT minus EI, where UT was the energy of the entire ensemble, and energy EI is the energy of system A when it's in quantum state phi I. Okay, and so this becomes gamma E to the UT over KBT, and if we separate the exponential into two factors, we'd get a minus e to the minus EI over KBT. Okay, and so this is the number of quantum states of the entire ensemble when UA is equal to EI. Okay, so what we're going to do next is we're going to say, well, what if we relax this constraint that system A has to be in a particular quantum state phi I? So then, to get the total number of quantum states available to the entire ensemble when system A can be in any quantum state, we just take this result and sum it over all of the possible different quantum state energies. So, it could be E1, E2, E3, up to however many possible quantum states there are. And the notation we'll use is that n total is going to be the sum of j of w e j. And so let's just remember what all of these things are going to mean. So this is the number of possible quantum states of the ensemble. Let's say for the ensemble, when UA is allowed to vary. So it could take on any possible value. And the sum is over all possible states of system A. Okay, but we just calculated this WEI. It had a bunch of constants, and so the constants can come outside the sum. The constants were gamma e to the UT over KBT. And then we have a second factor, which we can't take outside the sum, and so it's going to be e to the minus EJ over KBT. So now we have two possible results. We have results for the number of states of the ensemble when we pick a particular energy for system A, or choose a particular quantum state for system A, and we have the total number of accessible quantum states when system A can be in any of the available quantum states. So what we can do with that is we can say the probability that system A is in a state with energy EI is Well, it's the ratio of the number of states that are available when system A has energy EI divided by the total number of possible states. Okay, and so we have these results. The first one was gamma e to the ut over kbt, e to the minus ei over kbt, and then for the denominator, it was gamma e to the ut over kbt times the sum over j of e to the minus ej over kbt. The two prefactors are identical and they cancel. And the result is that the probability that system A is in a state with energy EI is given by e to the minus EI over kbt, and the denominator I'm going to just write as z, where z is equal to the sum of j, e to the minus ej over kbt. Okay, so these two results are important. This first one, for the probability, is the Boltzmann probability distribution. And the second result, z, is called the partition function. And so if you've taken some statistical mechanics previously, this partition function and Boltzmann distribution will be familiar to you. The partition function, you can see, is just the sum over all possible quantum mechanical energy states. So this is the sum over the quantum mechanical energy states available or accessible by system A. All right, so that's all pretty abstract, but what we're going to try to do is we're going to try to make a connection between the partition function or something related to the partition function and to macroscopic thermodynamic variables that can actually be measured. And so it's going to be pretty neat because we'll have a very direct link between the microscopic quantum mechanical states of a system and its macroscopic thermodynamic variables. Okay, and so let's start that. So we'll first start with the entropy. And the canonical ensemble. Okay, so we'll draw this kind of picture that we had before, where we have our ensemble where all of the constituents are in thermal contact with one another. And so maybe there's M members to this ensemble, and then somewhere in here is system A. Okay, and so we have system A, which is the red one, in contact with M minus 1 replica systems that together form a canonical ensemble. Okay, so we'll just emphasize once again that S equals KB ln W is valid for the whole ensemble because it is isolated from the outside universe. However, KB ln W is not valid for system A in the ensemble because it exchanges energy with adjacent systems. In other words, it's not an isolated system, system A itself. Okay, so now let's go back to think about this canonical ensemble that has M members. So of the M systems, let's suppose that Ni are in quantum state phi I. Okay, so some of the members might be in the same quantum state. So that is, maybe N1 of them are in state phi 1, N2 are in state phi 2, and this can go on for all of the possible quantum states. In that case, we can say that if we sum over all of those possible quantum states and add up all of the Ni values, that would give us the total number of members in our ensemble. So there are W equals M factorial over N1 factorial, N2 factorial, N3 factorial, and so on, ways to form this arrangement. In other words, there are lots of different ways to have N1 of the systems in state phi 1 and N2 of the systems in phi 2 and N3 in phi 3 and so on. And the way that you count those number of arrangements is through this expression M factorial divided by N1 factorial, N2 factorial, N3 factorial, and so on. And so if we wanted to calculate the entropy of the entire ensemble, we would have to take the ln of this W. And so the ln of W would be equal to the ln of M factorial minus the ln of N1 factorial minus the ln of N2 factorial minus the ln of N3 factorial, and so on. And so another way of expressing this is the ln of M factorial minus the sum over I ln Ni factorial. So what we're going to do now is we're going to make use of this should be a factorial. We're going to make use of an approximation to simplify this, and it's going to be Stirling's approximation. So we're going to use Stirling's approximation for large factorials. And so Stirling's approximation is that the ln of n factorial, or one form of Stirling's approximation is that the ln of n factorial is approximately n ln n minus n when n is a large number. Okay, so if we do that, then we could say the entropy of the ensemble, Sm we'll call it, divided by Kb is equal to the ln of W, which is approximately. So we're going to assume that the ensemble is very massive, so it has lots of members, and there's lots of those members that are in state Ni. So ln of m factorial is going to be m ln m minus m. And then we have minus the sum over I of ln ni factorial, which is going to be ni ln ni minus ni. Okay, and so let's see if we can manipulate this a little bit. So that's going to be m ln m minus m. So we didn't do anything there. What we'll do in this step is we'll distribute the sum. So we have minus the sum of I and I ln ni. And then we have minus the sum of minus ni, which is plus the sum of ni. But if we just add up all the ni values, we just get the total number of members of the ensemble, and the minus m cancels with this sum. Okay, the other thing we'll do is, for convenience, we're going to write m as the sum of ni. And so that allows us to express this entropy as the sum of I and I ln m minus the sum of I and I ln ni. So we have a common factor now. The sum of ni is a common factor, and so we could factor that out. And it's going to be ln m minus the ln of ni. Okay. So the entropy of our ensemble, our canonical ensemble divided by Kb, is approximately. So the next thing I'm going to do is I'm just going to factor out a minus sign. So we'll have a minus here, and then I'm going to multiply by m and divide by m. So there's my multiplication by m. And then we have a ni, and I'll divide by m here. So those m's cancel. And we factor out a minus sign, so I'm going to reorder the terms in the bracket as ln ni minus ln of m. Okay, so minus m, sum of I and I over m. In this step, what I'm going to do is I'm going to combine the lns inside the brackets. So ln ni minus ln m is equivalent to ln of ni over m. Okay, good. So we're very close to where we want to be. Next thing we'll do is we'll note that for large m, ni over m is, if we just count how many of the members of the ensemble are in state Ni, and m is a really huge number, then this ratio Ni over m tells us the probability of finding any one of the given members of the ensemble in state I. So this is Pi. So where Pi is the probability that any system in the canonical ensemble is in state I. Okay, So if we do that, what we could do is, let's write SM, the entropy of the ensemble divided by M. So now this is going to be the average entropy of a system in the canonical ensemble is equal to minus KB. So I'm going to multiply by the KB. And we divide it by the M, and so then we have the sum of Ni over M, which we're going to say is Pi. And then we have the ln of Ni over M, which is again Pi. And so now we can finally conclude that the average entropy of a system in the canonical ensemble is S is Sm over M, which is minus Kb, sum of Pi, ln of Pi. And so you can clearly see that that's different than what we had for the microcanonical ensemble, which was this Kb ln W. What's nice about this result is we know what Pi is. Pi is given by the Boltzmann distribution. We've already calculated Pi. So Pi is equal to e to the minus ei over kbt divided by the partition function. Okay, good. So that's an important result. Now, what I said we wanted to do is we wanted to come up with a connection between the microscopic quantum mechanical states of a system and the classical thermodynamic quantities. And so that's what we'll focus on now. So the connection between the quantum mechanical, let's say, partition function Z and classical thermodynamic quantities. Okay, so we'll start by taking the ln of this Pi, which is the Boltzmann distribution. And so that's going to be equal to minus ei over kbt minus the ln of the partition function. So we did that because our expression for the entropy includes this ln Pi. Okay, so therefore entropy is Kb sum of I Pi, and then it was the ln of Pi. I've left out the minus sign here. There's an overall minus sign that's going to cancel with the minus signs in this ln Pi. And so we get ei over kbt plus ln of z. Okay, so what is this equal to? It's 1 over t. For the first term, the kb factors cancel, and we have a sum of I, Pi, Ei, and then we have plus kb ln z sum of I, Pi. Right, ln z has no I subscript, so we can pull it outside the sum. If we sum over ei multiplied by the probability of a state being, the probability of a system being in state I, this tells us the average internal energy of a system in the ensemble. So this is the average internal energy of systems in the ensemble. And the sum of pi, if we just sum over all of the probabilities, we just get a 1. And so what we have, therefore, is if we multiply by t, we can say t times s is equal to this average internal energy plus, we multiplied by t, so we get a kBt times the ln of z. And so you could start to see what's emerging here is a relationship between the partition function and some thermodynamic quantities, temperature and entropy and internal energy. Or U minus Ts is equal to minus kBt ln of z. This UTS you may recognize. U minus Ts is F. It's the Helmholtz free energy. It's the average value of the Helmholtz free energy. Okay, so let's summarize some of the important results that we've obtained today, and then we'll continue with this, continue trying to develop a relationship between the quantum mechanical partition function and macroscopic thermodynamic variables. So, summary of the key results for the canonical ensemble. Okay, one is the Boltzmann distribution. So this is the Boltzmann distribution. The Boltzmann distribution involves the partition function, Z, and the partition function was kind of a sum over all quantum mechanical states. And so this is a partition function. We calculated the average entropy of the members of the canonical ensemble, and it depended on this Boltzmann distribution. And so finally we've got now this Helmholtz free energy. And so let's just emphasize that these are important results. Okay, so one comment is that this Helmholtz free energy can be measured / deduced experimentally. Therefore, the partition function is a link between the quantum mechanical energy states of a system and the macroscopic or observable thermodynamic behavior of the system. Alright, so we're nearly done with today's video, but let's just make a couple more points. To experimentally deduce this Helmholtz free energy, what you could do is, one is you could measure the specific heat or the heat capacity versus temperature. Two, you're going to use the relation that the heat capacity is du dt to find u. Okay, so you could integrate with respect to temperature to find u. And then three is you could use the relationship Cv is T ds dt to find entropy. So you would take your measured heat capacity, divide by T, and then integrate with respect to T to deduce S. And then you can find F is U minus Ts. So that's one path to get to the Helmholtz free energy. So the next thing we'll do is we'll just do a bit of thermodynamics now. The relationship, are the relation between this Helmholtz free energy, which is a function of the partition function, and other thermodynamic quantities. Okay, so we know that F is U minus Ts. So therefore, if we take a differential, we're going to get du minus Tds minus S dt. And du is Tds minus P dV minus Tds minus S dt. Okay, so the Tds cancels, and we're left with dF is equal to minus P dV minus S dt. Okay, then what we can do is we can say, well, P therefore is going to be minus dF dV at constant T. S is going to be minus dF dt at constant V. So we've already used that Cv is T ds dt with respect to V. But if we use this expression for S in here, we could relate the heat capacity directly to the Helmholtz free energy. And so that's going to be minus T d2f dt2 at constant V. Okay, and so there are some links between the thermodynamic quantities of pressure, entropy, and heat capacity to the Helmholtz free energy. So how about this internal energy? So we said U bar was Ts plus F. Okay, so therefore U bar is equal to, let's see, S is minus dF dt. So we have minus T dF dt at constant V for the entropy plus F. Okay, so let's next use that F is minus kBt ln Z. So that means dF dt, we have to use chain rule here, or sorry, not chain, product rule. So this is going to be minus kb ln Z minus kBt. And so in fact, we are now going to use chain rule. We're going to have derivative of ln z with respect to t. Sorry, we didn't actually use chain rule. We just used product rule. Okay, so therefore, if we go back to this internal energy expression, we have, for this derivative, we're going to have kBt ln z. So we have to multiply by t, this derivative that we calculated, by minus t. And so the first term becomes plus kBt ln z. And then we get plus kBt squared d ln z dt. And then we have plus f, but f is minus kBt ln z. And so now we get a cancellation, kBt ln z minus kBt ln z. And so therefore, the internal energy in terms of the partition function is kBt squared d ln z dt at constant v. So once we know z, we can calculate f, and therefore also PHYS, pressure, entropy, heat capacity, internal energy, and if there's other thermodynamic quantities that you wanted to find, you could probably develop the right relationship. Okay, and so let me just highlight one more of these important results. Okay, good. So that's what I wanted to say about the canonical ensemble. Looking ahead in the next video or two, we'll look at one more ensemble. We've looked at the microcanonical ensemble, which was a bunch of replica systems isolated from one another. Now we've looked at the canonical ensemble, which are a bunch of replica systems in thermal contact with one another, so that they're at constant temperature, but they can exchange energy with one another. We're going to look next at the grand canonical ensemble. And so what this ensemble will have is a bunch of replica systems in thermal contact with one another so that energy can be exchanged between the systems, just like we just treated, but will also allow particles to be exchanged between adjacent systems. And so we'll allow particles to flow into or out of neighboring systems, and we'll analyze that case in the coming videos. All right, thank you very much, and we will see you next time.